The final part of this course is about the energy of a simple harmonic oscillator. And as always in physics, conservation of energy is a fundamental idea. And you need to be able to apply conservation of energy to an oscillator. So let's look at, first of all, just an undamped simple harmonic oscillator. Well, the total energy of if it's undamped, it's going to remain constant. The total energy, there's none being removed from the system. But of course, a simple harmonic oscillator something's going on with the energy. If we just have a look at some mass spring system. So supposing we've got this horizontal oscillator, and I've drawn it there in 3 positions. The top one when it's at its maximum amplitude, the middle one when it's in equilibrium, and the last picture shows when it's at its maximum negative amplitude. Well, obviously there's something going on with the energy here. It would appear to have different amounts of energy at each stage. In the top picture, it's actually stationary at that moment. So, but of course, the spring is stretched out. In the middle drawing, it's moving really fast and the spring is in its equilibrium position. And so it clearly has kinetic energy, a lot of kinetic energy there. And in the bottom drawing, it's stopped again, so there's no kinetic energy, but the spring is compressed. So what's going on is the following. We can write down that in the top drawing, this has 0 kinetic energy, but max elastic energy, which is potential energy, stored energy. In the middle diagram, it has maximum kinetic energy, but because the spring isn't stretched or compressed, it has 0 potential energy this time and maximum kinetic energy. So all its energy is kinetic. And in the last diagram, it's back to the first situation where it's stationary again, so it therefore must have 0 kinetic energy. But the spring is mightily compressed to its maximum, so it's got maximum potential energy. So that's really interesting. And then any other stage, well, we can kind of imagine that it's somewhere between the two. I mean, if we imagine it just here on its way shooting back this way, well, some of that potential energy is being turned back into kinetic energy, and so it's lost some potential, which is turning back into kinetic. Let's see what a graph of energy will look like. Energy against displacement. So how does the energy vary through the oscillation? Well, we already know that the total energy, we've said, remains constant if it's undamped. So I can actually just do a straight line, horizontal line, bang. As simple as that for total energy. And of course the extremes of that line, if we just want to note them there, that's going to be, but it can only go from plus A to minus A. There is no oscillation outside of those, so I can't continue. So those will be the extremes of the line. But between plus A and minus A, wherever the oscillator is, this idea that there's no damping, the energy is conserved, means there's a straight line, constant value. But what about if I wanted to do a graph of kinetic energy? So we better label that one, that's total, so I'm going to do some more lines. So that's total energy. Well, if we want to draw the kinetic energy, well, okay, that's maximum in the middle, and we've already decided that in the middle there is no potential energy. And if there's no potential energy, all the energy must be kinetic energy, which means that it must actually go through a point here, because there is only kinetic energy, so the kinetic energy line must be all equal to the total energy in the centre when there's no potential. And of course at the edges we've already decided that there's 0 kinetic energy, so we know it goes through these 2 points here. Well, it turns out to be a nice kind of upside down horseshoe shape and symmetrical. Not that my diagram looks particularly symmetrical there. Well, look, we can analyse this a little bit more, because we can actually write an expression for the total energy, and we can say, well, the total energy of the oscillator is, we've already decided, equal to the kinetic energy plus the potential energy. So, and we've also managed to draw a line for the kinetic energy. Well, we also know that the potential energy then must be the total energy minus the kinetic energy. So if I do the blue line minus the red line, well, if you think about that for a bit, you'll discover that it's kind of like just a sort of flipped over version. And that makes total sense because we know that in the middle of the oscillation, the potential energy is zero because the spring is not compressed, and at the extremes the spring is either compressed or stretched, and so we've got max, and it's not moving, so there's no kinetic energy. So let's label these. So this is the potential energy line, and the red line is the kinetic energy line. Great, okay, so that's a classic graph. Questions like to discuss that graph. That's quite useful to know about. Well, we can take these energy ideas a little bit further and make them a little bit more mathematical, and we'll come out with a really useful little physics principle. We actually know, don't we, that because it's simple harmonic motion, we know that the force is equal to some constant minus some constant times the displacement. That's the definition of simple harmonic motion. If it's a spring, like in this case, then the K is simply the stiffness of the spring. But this is true for any system where K is some constant. Well, if you think back to the example of when you looked at Hooke's law in materials, then we know, don't we, that that the work done in compressing or stretching a spring is actually found by finding the area under a force extension graph. And so if that's our force at extension x, then the work done was the area under here, and that was given by, and you'll hopefully recognise the expression, that the work done was a half kx squared, or the area of the triangle. Well, that was true for, that's the potential energy stored in a spring, but so that would be, K would be the stiffness of the spring. But of course it's true for any, if F is Kx, then, well, that's identical to Hooke's law. So we can just have a general truism that the work done displacing a simple harmonic oscillator to a certain position x is a half K, where K is the stiffness if it's a spring system, or whatever other constant it may be for any other system, times the displacement squared. So that's the work done stretching or compressing the spring. So it's also the energy stored. So it's also the elastic potential energy if it's Hooke's law, or the potential energy if it's some other type of oscillator. So the potential energy, EP, we have an expression. Great news. So we have EP equals a half kx squared for any given displacement. Well, now we can do a little bit of a trick, because we know that at the extreme position, so when x equals plus a or minus a, then either of those positions, that gives us that the stored energy, the potential energy, is going to be equal to a half Ka squared. But of course, what the trick is that at that position there's no kinetic energy. So we know that then all the total energy is, the energy is all potential. So we can say that E total must be equal to EP when x equals plus or minus a. Yes, so just to sort of explain that once more, just so that's really clear. At either of the extreme positions there's no kinetic energy, but because the total energy is the sum of the potential and the kinetic energy, well, if the kinetic energy is zero, that becomes zero, and then we get ET is equal to EP. So that's what we're saying there. And we know we've got an expression for EP at plus or minus A, which is a half Ka squared. So we end up with the final statement that we can say that the total energy of a simple harmonic oscillator, which is undamped, must be equal, therefore, to the potential energy at the extreme, which is a half times K times the amplitude squared. Now that's pretty massive and useful physics principle, that the energy of an oscillator, the total energy of an undamped oscillator, is proportional to its amplitude squared. And it's true of a damped oscillator for any one moment at any particular given amplitude. And it's also good just to realise that this can be written in one other way. Just remember that, so I'll put here note, remember that K over M is omega squared. So we can actually rewrite that also as the fact that the total energy alternatively is a half m omega squared A squared as an alternative way. Yes, because K would be m omega squared if we rearrange that. Hopefully that makes sense. You might want to think that through for a moment. Okay, so, but I'm going to highlight this important equation, an idea, and the important idea that the energy of an oscillator is proportional to its amplitude squared. We'll do some questions, or you can have a go, and but I'll do some video solutions for them so that you can see how it works and what's going on.